I am Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at our terrace with Frank Schirmeister, going to talk today about the challenges of integrating RISC-V designs. Frank, no matter where you go these days, RISC-V is a presence. We're hearing RISC-V designs almost everywhere. But how do you integrate those? Because each one is very unique.
Well, the scenario as it typically goes, it's always product management's fault. So they read up that RISC-V gives you the freedom to innovate and to do your bespoke custom designs, optimize it for the workloads your company wants to do. And then the product management guy comes in and says, well, I have it all done for you. I licensed the RISC-V core. I licensed all the other peripherals you need. So just go ahead and integrate it. And it's typically not easy to do that. So that's what we're talking about here today. Let's look into more detail.
Frank, what are we looking at?
Well, the evil product manager came in and said, I'm building this machine learning accelerator with some vision components for automotive. And the product manager basically says it's all figured out, right? So you have a couple of RISC-V cores here in your compute environment, some caching going on. So I'm drawing two clusters here for this, right? So then you have some domain specific, like some accelerators going on here, accelerating functionality. That's often kind of a secret source of things. And you have some, like let's say some image processing going on with ISPs. You have a machine learning subsystem. Often you find these to be these rather regular structures. So I'm not drawing them out here. You have a safety island if it's automotive. Then down here you have the memory. So the green part is the chip. So you have outside DRAM going in here. And that's connected to your memory controller here on chip. You have high-speed wired interfaces, wireless stuff. So you have all these blocks going on. You have wireless transmission for Wi-Fi. You have a security bit, especially in automotive, very important. You have all these subsystems, if you will, I/O, HDMI. It's somebody wants to play and display everything. So that's all the blocks. So now how do you connect them up inside and then even across the chip with chiplets?
The challenge here is that these do not connect in a very standard way, right? Because each piece is almost like what you're doing with chiplets, where each one is going to be unique. Each one is going to have its own characteristics.
Right, so the two big items to consider first is like who is actually sharing memories, right? So this guy here may share with the compute subsystem this memory here, right? So you have cache coherency to be considered with these caches here coming from the compute subsystem. You have a bunch of other pieces that are more important to look at from a perspective of latency, throughput, predictability. So this is what we call the non-coherent bit. So this would be non-coherent, and this would be, the other part here would be coherent interconnect. So now that's a high-level picture. Who actually needs to talk at which level? Who needs to talk coherent or non-coherent to each other? And then one thing you pointed to with your questions already is these guys, when you license them, they may have all different interfaces. So here you may have something like a chai.e interface or chai.b. Here you may have a bunch of AXI. So typically you actually find in these subsystems your own sub-networks non-coherently. So those are the non-coherent networks in here. And here you speak things like AXI, you speak things like OCP. There's also then another coherent protocol here. There's ACE going on. That should have been blue. And so you have this protocol salad of all these different protocols you need to be aware of. OCP is another one of them, which is a little bit older. They're new, emerging. They are like variants which then connect to things like CXL, for example, for the outside connection, and PCIe. So it's a protocol salad to deal with. So one of the challenges is how do you bring them all together for the coherent and non-coherent bits of the chip?
And so, how do you do that? Because that is one of the big challenges.
We, as a NOC company, a network on chip company, we have all these protocols learned, if you will. We have specific interfaces for our NOC, which takes the different interfaces and unifies the protocol salad and allows you to combine everything, both in a coherent and in a non-coherent fashion, and then have an internal protocol that carries all that along and translates it for it. So you, as a designer who just figured out, I have this really cool new freedom to innovate RISC-V modification of my core, you don't need to worry about the protocols of all the other components you integrate with.
So, what happens when you get into, say, a difference between a planar chip versus 2.5D versus 3D or some fan out, fan in? You've got all these different possibilities that are out there these days, and each one is a little bit unique.
So that's a challenge kind of stacked on top of it, pun intended, where you have the potential product management requirement that all of this has to go across chiplets. So you have a chiplet interface here. So you may go over UCIe between them. So now you need to figure out how your memories are, for example, shared. There are different configurations you need to deal with. Over here, this partner for the chiplet scenario may have to access your memory. So now all the snooping that goes on in coherency needs to be carried across the chiplet boundaries and so forth. That becomes very complicated. That's kind of the fourth step, though, because unification is the first bit, trying to make sense of all the blocks you have licensed and connecting them. Connecting things up within the systems is the second item, right? So if you have all these RISC-V cores, or even here the accelerators, often these are DSPs, and then the machine learning elements, you need to connect them. For machine learning, you not often need coherency. These guys basically get their data presented to them. Here it's more important about things like broad width in this mesh, where we can essentially here connect in a mesh form in a non-coherent way with our products the different processing elements up. So these connections need to be done first before you even think about the connections to the outside, which is really an architecture choice, because this might just flip on the other side, and you need to figure out which of these protocols do you then actually package and transmit over the chiplet interface using UCIe, perhaps with a CXS streaming interface. So that needs to be done at a top-down architecture level.
And to some extent, what you're doing here is really enabling the democratization of the design here, too, right? Because most companies that are going to be developing this do not have this expertise internally.
That's right. So if you look into how this all evolved over time, when I started in my first jobs back in Germany still, we just had invented the VSI Alliance, the Virtual Socket Interface Alliance, that later became Spirit and Accelera and so forth with IP Exact. And that was early on a way to connect these things up. And then ARM, gotta give them credit, had a lot of to do with things. They invented Amber in the mid-90s. That was about 200-300 pages of spec. Today, if you want to understand all these, those are thousands of pages of spec. So you really don't want your teams, as they are figuring out the differentiation and want to deal with the software and the right final modification of the tuning of the RISC-V cores, you don't want them to be distracted with having to learn these protocols and how they all connect, what potential interface considerations you have to make. We have done all that, and that's what we call here the de-risking of the projects, because you really can focus on your differentiation in what you're building at the systemic architecture level and at the differentiation level with your accelerator, the software on it, or with your compute subsystem on it. So de-risking of those projects is very important.
One of the challenges as you move forward into things like RISC-V, though, is and heterogeneous compute in general, is that you're mixing a lot of things in terms of partitioning and prioritization. How does that work with a NOC?
Well, you have to make some system architecture decisions, and I think the kind of hidden secret, what's often forgotten in today's discussions. There are really three level of chiplet connections, right? So they're actually out there for quite some time. If you look at the big players like the AMDs, the NVIDIAs, the Intel, they control all of that, right? So they say, we just need our phi here, just of course in air quotes, we just need our phi here for the eye diagrams to work on the other side of my design as I connect things, and they can decide the protocol that goes in here. These things are called flits for the streaming. Those are the serialized protocols. And then you have a protocol stack where you basically say, okay, here I have, for example, a CHI, the coherent hub interface from ARM going in. I may have CXS here, and then I have UCIe, or to be fair, a bunch of wires to go over here. So as I consider all this, I now need to understand, will these actually both have to access this memory? Then cache coherency needs to play, and then all the effects like snooping and so forth need to work. Those are all built in the TRI protocol, that you basically figure out who has the last valid item in the caches, and then a whole lot of coordination goes on. It's a huge difference whether you have a cache hit or cache miss, right, in terms of performance. If these don't have to share this all the time, and if they don't have to be fully symmetric, meaning this guy also has this DRAM and we need to look at both sides, you have subsets of coherency like I/O coherency. So it needs to be architected right at the system level. For us as a NOC, it becomes kind of super NOCs, right? Because you now need to decide this NOC here, I have to have a flipped version here to talk over this, and you need to take into account the latencies, the bandwidth, and so forth from a systemic architecture level.
So you've got all these things connected. Now, what do you really have to think about from a RISC-V perspective as you're designing these chips?
So beyond the NOC, beyond the interconnect and the protocol you choose wisely, right? CHI, ACE, AXI for the non-coherent parts here. You need to really understand the ecosystem of the RISC-V core too, right? So connecting it sounds easy at first sight, but there are other things to be considered. So for example, debug, right? So there is when you look at the RISC-V standardization, they look very much into things like trace to understand the data flow throughout the chip. And that's something which in other ecosystems is kind of provided together with the core. In the RISC-V ecosystem, as it is a standard and an open ecosystem, these need to be considered. Same things around the memory interface, the IOMMUs, how you deal with the memory interface. How do you do simple things in air quotes like interrupts, like, so you have these interrupt controllers that need to work, and that you have your RISC-V processors to react to them completely, right? So or consistently across different cores. This might be one vendor, there might be another vendor here, right? So there are a lot of ecosystem infrastructure items beyond the pure protocol to be considered. So it becomes very interesting very fast to integrate all that together. And again, from an ecosystem perspective, we talked earlier about the different sets of chiplet scenarios. If I own all this, if I'm the master of all things going on, I just decide, I use this, I use that. The whole promise of the chiplet ecosystem, to go back to that, is that you actually take your chiplet and you get it into multiple designs, kind of like PCI Express works today, if you will. Well, plugfests are not that trivial to do. You have to integrate it, test it, and in that context, you need to agree on a lot of things for these data to actually be in a correct protocol, packaged, transmitted, and so forth. So for a full open ecosystem, a lot of additional items need to be considered so that you can have your chiplet and then get it into many designs for differentiation.
And a way to think about this is that you're no longer just looking at a stacked die, you're looking at stacks of stacks, right? And you're
Correct.
trying to integrate each one. Each one of those stacks may be very different.
That's absolutely right. And you have then on top of it different protocol stacks, right? So the whole stack, all the way to the software and how you program this and so forth, becomes very interesting to deal with, because this compute system may have to access in a fully symmetric way another DRAM over here. So that becomes very fast, complicated items. That's why we see different topologies. And that's very important in our NOCs here. We support different topologies. We go from mesh and flex NOC here to various asymmetric irregular topologies, where you can basically decide, I have a very fast line going in here to the fast wireless or the fast wired, but I have a slower line going on to some peripherals or other aspects of the design. So that is all becoming a very important aspect as you plan that across chiplets.
And even beyond that, as you go into this, you're looking at it from the standpoint of, from an architecture standpoint, the thermal issues. You're looking at all the short channel effects. You've got a whole bunch of physical effects that you didn't deal with before. All that has to be built in here, right?
Yeah, and think about it, right? So if this is just my functional diagram, which the product manager has put onto the whiteboard, literally. So now that becomes at the end the layout, right? So I have my different placed components. Now the poor NOC, to claim a little bit of misery here, has to basically fit into the bits between the floor plan blocks for of those items here, right? So now it becomes a question, how long are my wire delays? How many pipeline stages do I have to insert? Those are things which we consider early on in the NOC development process. And you can imagine, we are not quite there yet, but you can imagine things we predict early, if you will, estimate early by saying, okay, if the machine learning subsystem and the computing subsystem and they all access the memory, if they are too far away from each other, what does that mean for the metal I create as I connect everything up? And you can imagine even here having software running on stimulating essentially the wires, mean at the end the copper metal on chip. How do I stimulate this? And you could actually look into heat maps early on, right? Because we know, for instance, where in this coherent or non-coherent bit, let's take non-coherent, where my different switches, my buffers, the different elements of the NOC are positioned. I can actually tell the layout tool, and we do this today, I can tell them, well, I have switches here and here, thinking of this more as a layout now. We give this information down into the digital implementation flow. And with that, you can then, as you pointed to thermal, you can eventually early on decide, okay, let me look at this, what type of data, how much switching is going on, what thermal effects can that have, and then be smart and move it away from some of the hotspot areas early on.
Frank Schirmeister, thanks for a great explanation of a very complex subject.
Thanks for having me.